transportation?
IPsec tunneling and IPsec transportation. When you saw IPsec, I told you that if you have like a collection of networks and you have a source and destination, you have to, when you run IPsec, you have to have what? A security association established between the two end cores which are trying to communicate, right? So if IPsec, if the end host can run IPsec, okay, so basically you establish an IPsec security association between the two end hosts. So then you are set to operate in transport mode. Okay. On the other hand, if the host computers are not capable of establishing an IPsec security association on themselves, they have to go through this gateway routers. Okay. So in that case, the security association is established between the gateway routers. So which means this gateway router for this network and this router for this network have to establish an IPsec security association between themselves. So if you have to go through that, you have to also go through this IP encapsulation. And all packets going from this network to this network will appear to go through this tunnel, which is this IPsec security association, going from this network to this network. Every packet has to go through this security association between the two gateway routers. So that's why it's called tunnel mode. Okay. Now, what we mean by this IP encapsulation is
The source destination and the source and the destination IP addresses are encapsulated into another datagram.
Right. So the datagram coming from this end host, source and destination. Okay. So it will look like something like this. So the IP address of the source, IP address of the destination. So this will be the IP header, and say some TCP header, and then your data. Now we cannot send this as it is because it doesn't have the IPsec header. So the two end hosts don't support IPsec. But you want to send through IPsec connection. So what you do is you could even encrypt the whole thing. So this is your IP datagram. You could encrypt the whole thing because you're going to encapsulate this IP datagram inside another IP header that has the IP addresses of the gateway router. So let me call it as A and B. So the IP address of the gateways. Still, we have not used IPsec here, but this is at least this is the solution if you want to communicate between two private networks. So this will be used for like establish a virtual private network. Now, when you want to go through IPsec connection, you establish an IPsec header, and then you have the IP addresses for the gateways. Okay. So the whole thing appears as the payload for the IP datagram. Okay. So the routers that are on the internet, as you think that these two gateways are the end hosts that are communicating. So that's what all the other intermediate networks will think like. So once a packet gets to the final destination gateway, this will be removed, this outer IP header will be removed, and then the inner one will be brought forwarded to the destination. So until then, for all these intermediate networks, everything will be encrypted. So encrypted by a key that is not only by these two gateways to decrypt. So nobody else in the intermediate networks will be able to decrypt and find out what is inside. Okay, so since we are encapsulating one IP datagram inside another IP datagram, it's called IP encapsulation. So whenever you have a tunnel, they go together. So basically trying to, it's like you have, having gone through Pittsburgh and all these areas where you have to go through a tunnel and then come up, right? So So you never know what is happening inside. It's like a black box. So all these things, right? All these hosts assume that they are connected to these through a tunnel. So they don't need to worry about all this IPsec header. All this IPsec business will be handled by this gateway. Okay? So for them it looks like a black box. They send to the gateway and the gateway handles all this IPsec security association. Similarly, the end gateway here handles that and they get packets in a secure form. Whatever they're trying to exchange is not being looked at by anybody else. That's what they want. They want to exchange packets in a secure fashion and maintain confidentiality and all those things. So without going through IPsec by themselves, they can manage that by operating this tunnel mode. Okay? But the only drawback is within this network. So if there is a malicious guy, an insider, so insider attack or something like that, if some host here is malicious because the data coming from this host to this gateway is still in plain text, it could be exposed. So that's the only drawback of tunnel mode, or probably one of the main drawbacks of tunnel mode. So any malicious attacker inside this source network or similarly the destination network would get to see what is the data because it's not encrypted. Okay, so it's encrypted only from here.
Okay.
And the gateway could be a bottleneck because it could take some time, because if all hosts are trying to go through this gateway, this tunnel, then the gateway has to do all this encapsulation business for every packet, so it could take some time. So that's another drawback or weakness with the tunnel. On the other hand, it's more scalable because you don't need every host to be able to handle IPsec. So if you go for transport mode, every host in the internet should be able to handle IPsec on its own. It's just not that easy to expect. So on the other hand, if you enable the gateway routers to just be able to handle IPsec, it's more scalable. Like we can use this tunnel and have every host be able to communicate securely.
Thank you.
Okay. Alright, so I explained it again, which I have explained before too, right? I could ask this in the final, right? Okay, so have you probably should have connected your laptop to your wireless LAN, right? So what do? You look for the available what? Networks, right? So you probably remember now some names, isn't it, of your LAN? So that is called the SSID, Service Set Identifier. Okay? So 32-bit unique, 32 character unique identifiers. Okay? So that uniquely identifies a wireless LAN within that area. Okay, so all the like if you're staying in an apartment or something, each one will be having their own SSID, each apartment person, right? Like different apartments have their own one. So you'll have to pull out that list and select which wireless LAN which you want to connect it to, right? And most of the time they have a password, so you can't just connect to that. So you have to get validated to a username and password, right? Password. Now so that's why the wireless LANs within a particular area have to have a unique SSID. But just because you know the SSID is not any form of authentication, because anyone can know what are the names or what are the wireless LANs available in that area. Okay? So that's why in addition to knowing the SSID, you need to know the password to connect to that wireless LAN. Okay? Now, so one thing you have to also remember in wireless network is it's not like a wired communication where the hosts are connected through some dedicated wires. So which means whatever I send is sent only on this wire. So if someone wants to hack, means they have to be able to run some hack the channel, means they have to be able to kind of have something to listen to what is being sent on the channel, right? But in a wireless, it's more easy because it's the broadcast. It's like outside in the air, right? So if someone can receive your signals and they can tune their receiver to the frequency at which you are sending, they can kind of find out what you are sending. So that's why it's very important to encrypt all your communication in a wireless medium. So it's not really recommended to send anything out in plain text. Okay? So it's a broadcast medium. Most of the time, whatever I send goes to everyone. So in a wire, I can say I want to send to that particular computer. So I send it on that particular interface. Whereas here I just send, and whoever can tune to that frequency can receive that. Okay, it's up to them to accept or discard it, but they could receive it. Okay, so that goes to two particular things. One is called stealth mode. So stealth mode is if you could operate without anyone else looking, knowing that you're operating. It's called stealth mode, or sometimes called promiscuous mode. Okay. So promiscuous mode is nobody else knows that you're listening to a channel at that frequency, and you just capture all those packets. So Wireshark is an example of operating in promiscuous mode. You run that, and you capture all the packets going in the Ethernet, so that is said to be operating in promiscuous mode. Okay. The same thing with that wireless LAN. If you're trying to connect, so most of the time the access point will broadcast. This is the SSID of this wireless LAN, and all the laptops, client computers will try to see if it can see that SSID. So that is called open mode. So the access point broadcasts its SSID information. Whereas in the closed or stealth mode, the user picks up an SSID. So the user requires a particular access point to connect to. Okay? So that's the difference between operating open mode and closed mode. Okay, so now let's look at how you might have heard of this WEP standard for wireless communication. So it was designed to provide security for wireless communication. Okay? It's not used that commonly anymore because we see it has some weaknesses, flaws, but this was kind of a beginning protocol proposed in the early days of wireless networks. You might have heard of this IEEE 802.11. So all the wireless protocol standards have this 802.11 extension. Okay? So now we have all this GI and all those. So every time they extend something, they add an alphabet, 11, then 11A, 11B, 11C, 11GI, and so on, all those things. Okay? So WEP stands for Wired Equivalent Privacy. Okay? Now one thing you should know with wireless devices is they do not have all the resources that you have with a desktop computer or even like a laptop computer. So if you're working with the phones and all those things, they have their own resource constraints. Similarly, a laptop should also have its own resource constraints compared to a wired computer. Okay? So which means all the encryption algorithms that you could run on your servers on a wired network may not be it may not be possible to run on a wireless device. It may have its own processor constraints, it may have its own memory constraints and all those things. And bandwidth is also a constraint. So you don't have dedicated wires connecting the computers. So the bandwidth available for wireless network is also a constraint. Okay, so if you could have used SHA and all those very complex hashing algorithms that produces like a 256-bit hash or a larger hash value in a wired network. Similarly, RSA, DES, and more powerful encryption algorithms. But in a wireless device may not be able to even run such encryption algorithms. Okay, so it may take a lot of time. So that's why you go for more simplified encryption algorithms and hashing algorithms when you go with wireless devices. So that comes along with the weaknesses with those algorithms. So that's why it's not a wireless network is not that secure. Okay. So this wired equivalent privacy uses one particular encryption algorithm called RC4. I could look up. So you could look up in Google what's the full name for it. But this is the name of the encryption algorithm. And the hashing algorithm it uses is very simple. It's the CRC algorithm, cyclic redundancy check. And if you know what CRC is from the networking course, it's like a checksum or an algorithm to compute a hash value. Okay, and it uses a 32. It produces a 32-bit hash value. Okay, so that's why it's called CRC32. Now this RC4 could be run depending on the size of your password key. So if your password, the larger of course you use is more secure, but of course the more time consuming it is. So if you use a 256-bit password, Actually, a password only like there's a difference of 24 bits. So your password is of length only 232 bits. Plus some 24 bits, you'll see what is the 24 bits, will make up 256 bits. Similarly, one more 4-bit password for another 24 bits will make 128. So you can have WEP versions which are like 40, WEP 104, all these things depending on the length of your password. Okay? So the way it works is, it takes what is called an initialization vector. So RC4 algorithm, we're not looking at the algorithm, but you just look at some black box and what goes inside and what comes out. So it takes the initialization vector and a key. So it could be like a 40-bit key, and this initialization vector is 24 bits. So together it is 64 bits, and then you are plain text. So all these things are input of the algorithm, and then you get your ciphertext. Okay. And the way it is sent actually is, the ciphertext is XORed with the plain text, and what you get out of it is what is being really sent. Okay, so you can say ciphertext, and this is ciphertext prime or something. So this is the real ciphertext that is being sent. So you don't send whatever comes out of the algorithm, you XOR it with the plain text. You know what XOR is?
Exclusive.
Exclusive OR. So it's different from OR. So XOR means one XOR is one is Y. Or in general, X XOR is Y. You get what? 0 if both are
The same.
interview questions.
Say it one more time for me.
Two binary variables, X or Y, taking value 0 or 1, right? XOR, you get 0 if both are same. Okay? And you get 1 if X not equal to Y.
Okay.
Okay? So that means 0 XOR with 0 is what? 0 XOR with 0 is?
1.
0. So the 2 bits have to be different in order to get a 1. The 2 bits are the same, it is 0.
Okay. I got it. Absolutely.
And XOR has this property, if you take up one of these and XOR with the result, you should get back the other one. So 0 XOR with 0 is 0, 1 XOR with 1 is 0, 1 XOR with 0 is 1, 0 XOR with 1 is 1. So you should get back the other. Okay? So it's not commonly used in all the encryption algorithms. So likewise, when it is about to be decrypted, what do? You try to pass the ciphertext back, but you have to be able to use this and feed in the decryption code of RC4, okay, and then again the initialization vector and this 40-bit key to get the plain text. Okay. Now, where is this drawback? This initialization vector is chosen by the sender randomly. It's a 24-bit value, but it is chosen randomly. So when you want to decrypt it, the receiver has to know what 24-bit initialization vector you used. So typically what happens is, you send the 24-bit initialization vector along with your ciphertext and your hash value that is computed using the CRC. So, but the CRC is not that powerful, it's only 32 bits hash value. Okay? So anyone who can listen to the channel can get to know what is this 24-bit initialization vector. So if they can, of course it's randomly generated, but the 24 bits, you may think it's still a lot of randomness is there, but 24 bits is not that big of address space to get random numbers. So if you can collect the ciphertext values for the same 24-bit random number, for a particular 24-bit value, you can get all the ciphertext values, you can do some cryptanalysis, okay, and try to find out what would be the key that would have been used. Because if for a fixed set initialization vector, the only thing then that varies is the key. So you can do some cryptanalysis and try to find out what is the key. Okay, and the key again is not that large; it's 40 bits. Or even if you go for larger values for the key size, it's RC4. It's not as complicated as RSA or DES. So it's a very simple algorithm the wireless device can handle. Okay, so it has its own weakness. Yes.
I'm gonna ask you, and I know it's gonna be wrong. I got confused when you went through that. You lost me like on the second step. I mean, when you went to the plain text and you got the 40-bit key, from that point on, I got a little bit confused because you got one going down to the ciphertext and you got one going to the RC4, and that's why I got confused then.
Okay, so this is how the ciphertext is generated. So you have a 24-bit initialization vector and a secret key that is known to only the wireless device and the access point. So remember, all communication is from the wireless device to your access point. Okay? So you want to send that securely. So you send your plain text, all these three are input to the algorithm, and whatever comes out is XORed with the plain text.
Okay, that's right. Okay.
And then whatever comes out of this XOR operation is what you are really sending.
Okay.
Okay. Now, so this is one weakness. So since you have to send the initialization vector along with the message, and the initialization vector is in plain text, anyone who can listen to the channel can get to see what is the value of this 24-bit initialization vector. So they can subject the ciphertext to some cryptanalysis and try to find out what is the key. Okay. And not only that, as I explained here, this is if you want to really send a message. Now, when you're trying to connect from your wireless device to an access point, you have to authenticate, right? Because you have to submit your password and all those things. So it goes through what is called a four-way handshake mechanism. As part of this four-way handshake mechanism, the first step is you're trying to send a request. Okay, I want to connect from this client to this access point. So you send a request, and this guy sends back a challenge. A challenge could be some integer something that you have to work on. It's like this nonce thing. You have seen this nonce approach, right? So it could be like a nonce, and you have to say that in the case of nonce, you have to increment it by 1, and you will encrypt that with the secret key that is like the password that you share between the client and the access point. Okay, and the access point will decrypt with that key and make sure you did the right operation on the nonce, on the challenge, because this is basically a response. So your response has to be a particular valid response for the challenge. And if that response is a valid response, then it will say okay or something to authenticate the connection. So that's a four-way handshake.
But with the nonce, you had the public certification to get that number. How does that number gonna get to the other point?
What do you say, public key?
Remember with the nonce, when you showed us the nonce in the screen, the public certification gave that to the other party. How does that number gonna get to the other party there?
No, the nonce is trying to make sure that you the client is the right person who knows that password. So you are communicating with the right client. That's what it is. So the way it works is, so first when the client sends its request, it will send its kind of IP address or some kind of username, right? So that I'm trying to connect to you. So the access point will send back a challenge like a nonce trying to figure out that you know the right password of that client, of that username, right? So now you have to encrypt that nonce, kind of increment the nonce by 1 or something, and then encrypt that with a secret key, like your password, that is known only to the client, and of course the access point should know that. So if you don't know the secret key, then you'll not be able to do a proper encryption. Okay? So the access point will decrypt that with that secret key and see if it's the right nonce. So if you encrypt with the wrong secret key, then the access point decrypts it, the nonce value won't match. So that's how previously I have asked you how you use the nonce to authenticate whether you're communicating with the right person on the other side. Okay, so when you encrypt with the secret key, you have to know the right secret key because the other side is going to apply what it thinks is a secret key for you. Right, so you got the experience in RSA project. When you don't use the right key to decrypt, you basically got some garbage. Right, so when this guy encrypts with some wrong key and the other guy uses a different key to decrypt, it won't see the incremented nonce value to be some garbage. Right, so that will be an indication that the other side didn't know the right key. Okay, so you have to use the right key to encrypt your nonce value. Okay, but the drawback with this approach is the nonce value, the challenge, is sent in plain text.
So how's that authentication?
No, it's an authentication because the encrypted version is the incremented nonce is sent as an encrypted value, right? So it can authenticate the other guy, but when it's sent as plain text, anyone can look at what it is, right? So what could happen is someone could collect. So it's not a drawback right away, but someone could collect all this encrypted this encrypted value, right? So basically, someone who listens to a channel can have what is called the plain text ciphertext pairs. So P1, C1, P2, C2, and all these things. I don't know whether we did this project. I could have assigned in another course. Where you have known plain text ciphertext attacks. So you have a collection of plain text and a corresponding ciphertext. Because the nonce is in plain text, right? And you get to see what? The encrypted version of it. All you have to figure out is the right key that was used. So you get access to both the plain text as well as its ciphertext. The only thing you have to figure out is, and you know what encryption algorithm is also used. The only thing you have to figure out is the key that is used to generate that ciphertext. So if you could continuously listen to that channel and capture all the plain text ciphertext pairs, right? So you could do some cryptanalysis. Like in the project I used to assign, that was your Caesar cipher and some simple encryption algorithm. You could really find out what is the key that is being used if you know the plain text ciphertext pairs. Okay? So that's called a known plain text ciphertext attack. So there are different ways of doing cryptanalysis. This is one way of doing cryptanalysis. If you know both the plain text ciphertext, not only just one collection of plain text ciphertext pairs generated the same key, the same encryption algorithm, you can do a cryptanalysis and try to find out what key is being used. Okay? So that is the big weakness of this WEP. The challenge is sent in plain text, and someone can capture all this plain text ciphertext pairs and try to find out the key. And if you know the key, then you can break in the RC4 and you can even find what plain text is being sent as part of the data. And then you can even change your hashing algorithm, so the integrity could be affected, because if you could find out what is the plain text, you could change it and encrypt with the same key, and then with a different plain text, of course, and then compute the corresponding hash value. So the whole thing will collapse. The integrity will be lost, the confidentiality will be lost, and all these things. Okay? So if you can do cryptanalysis here with this and with this RC4 by knowing because the 24-bit initialization vector is sent in plain text. So that's another weakness. So these two weaknesses put together will make you to be able to find out the key. Okay? So